So one of the viewers has sent in an Atari Lynx 2 to take a look at. It has an issue with the screen. So before we get into that one, I thought it's worth taking a look at the Atari Lynx 2 and how it handles power. It's always the place to start with any console and any diagnostics. So we're going to take a look at the Lynx 2. When the batteries provide power, where it goes into the system, and how it turns the system on and off. Because the Lynx 2 in particular has a very intermittent, shall we say, and complex power-on system. It uses a bunch of buffers, inverters, and a latching mechanism to trigger when the system's going to turn on. It's not a great design, it's not efficient, but this is a perfect little example to dive into how some of the hardware works and explain it to you. I will show you the scopes, I will show you the system working, and I also have a board here that I have that simply doesn't work at the minute on boot. So it's the perfect time to show you how the system should work, and we'll diagnose this board at the same time. So I've got here an Atari Lynx 2. I've taken all the parts off, just removed it from the case, and attached a few wires to help us diagnose. So you can see here we have the batteries coming in. So this is the negative and positive spring into the system. I've attached a wire here to the negative so we can attach our scopes and power leads and things. And then also for the scope, I've gone ahead and pre-attached some wires to this transistor here, this Q7 transistor, because this will be the one that will show us how the power on sequence should work. The screen is normally attached here, and the connector, the ribbon cable at the front, is attached here. So if we flip over and we take a look, here is the connector for the ribbon cable for like the power on buttons, the flip buttons, and all the controllers and D-pad. And here's the connectors for the ribbon cable. So the power on ribbon comes through pin 6 and 7. So you go pin 1, 2, 3, 4, 5, and then it's these two, 6 and 7. One is called power com and the other is called power on. So one's common and one's power on. So when you press the power button on the ribbon, if it's functioning correctly, it shorts these two connectors out here, which we can simulate by just shorting with a pair of tweezers like this when we want to boot the system. The way the Atari power system works is to basically isolate ground and then switch ground to the rest of the system when it's turned on. And it uses then a diode, which is D13 here, to drop the voltage. So it basically passes either the DC jack or the battery voltage into the system, but instead of lowering the battery voltage using switching, it just shunts all the excess voltage through a Zener diode. It really isn't very efficient. And then to turn on and off the system, it isolates ground. This can cause some interesting issues when debugging and fixing the console. So it's important to understand how this works, hence the reason for showing you this first. So to explain more, let me just pull up the schematic and we'll walk through this step by step. So we have here the Atari Lynx 2 schematic, and it's only a single page schematic. It's fairly simple design in general. You can see here is the DC jack for the power input, and then here is the battery. So the battery is these two springs that we're on about here. So we have the battery spring here. You can see the power then, which the positive of the battery here would be typically 9 volts. Comes along and through, and if you follow this line, it keeps going and going. Whenever there's no dot and lines cross like this, then these lines aren't joined, they're simply passing. When there's a dot, it means the line's joined. So far the power comes into the battery, up, through, keep going, keep going, keep going, keep going, and then you see it basically says 5 volts. So you might be wondering how there's 5 volts here when the input is the battery directly. There's no voltage divider, there's no reference, there's nothing going on. The key is here we have a Zener diode, a 4.3 volt Zener diode, which basically means it will let any voltage pass through, and once it's above 4.3, it will shunt that voltage to here, which is ground. This is not technically direct ground, this is a switched ground through Q12. But for the most part for now, just think of that as ground here. So the Zener diode has ground, and above here is connected to the 9 volt input or the battery volt input. So whenever you use a Zener diode, it's like a really cheap and inefficient voltage regulator. It's going to simply shunt the excess current through the diode, so the diode's going to get warm, burn power that it doesn't need to instead of it being properly regulated, and it would maintain the voltage at 4.3 volts if it wasn't current limited. So because of this current limiting resistor here, it will also float the voltage anywhere around 5 volts, anywhere from 4.3 to 6 volts. It's not really regulated, it's just shunting power. So the output of the system is, in essence, if D13 fails, would just output 9 volts straight to the system because it's not going to get shunted. So that means this entire system needs to be 9 volt tolerant. So that means all of the CPU, the RAM, everything connected to the system ideally needs to be 9 volt tolerant, because one failed component in this design and it would output 9 volts to the system. So let's take a look at what happens. You can see here this is battery ground, which goes through the DC jack back out and is also then reverse diode protected through D10. So if you insert the batteries back to front, this diode will protect. D10, you can see on the board, is up here. So we've got D10 there. So that's your reverse protection diode. D9 here, which is the one above, prevents the battery power going backwards into the DC jack. That's all that's for there. After that, the battery comes along, and then we get to this Q7 here, which is the main one we will be scoping to see what happens. You can see the gate, or in this case the base, because this is a PNP transistor. The base of this transistor is pulled up to the battery voltage, or let's just call it the input voltage for now. It's pulled up permanently to the input voltage, and it looks like it's pulled down to ground here, but it's not actually pulled down to ground. This symbol here, if we look, the battery negative here comes in and is labeled VSS, but it's not actually connected to the triangle ground symbol. We're carrying along the bottom, it goes through Q12, a transistor, looks like a MOSFET, and then through an inductor, and then we get to the reference ground. So this is the system ground. So the system ground is disconnected from the battery ground through Q12. So what this means is the base of this transistor is pulled high to the battery voltage at the moment until Q12 turns on and provides a reference ground here to pull the base down. I'll dig into hardware more as we go, but just as a quick point of reference, a transistor in general will have a place it's providing power from. So in this case, it's the emitter, which is always symbolized on a PNP or NPN transistor as the line with the arrow. But we have the base here, or the gate, depending on the type of transistor. We have the emitter here, or source, and we have the drain or the collector down here. So you can think of it as, in this instance, this is a PNP transistor. This wire here, which goes to the not power on line, which basically will mean when it's low, it's powered on, when it's high, it's powered off. So it's an invert. When you see this forward slash or an under or a line above the text, it means inverted typically. So it means when this pin here is a higher potential than the gate or the base, or the other way around, you can think of it as when the base or the gate is lower potential than the emitter or the source, then it turns on and acts similar to a switch. So it will join these two lines together. So for our simple analogy for now, we can think of when this power on not line here is higher than the base here, then this line from the power on not will join straight to this on low here. So it's like we've joined a wire between these two. And so all we need to look for is the base of this transistor pulling low. We can see from that it would pull low if it had reference to this ground here. So let's just start with the actual power button and trace it that way. So when we join pins 6 and 7 together on the cable here by pressing the power buttons, what's happening? Well, in the schematic, if we scroll over, we can see the thing called sub-PCB here. And you can see power COM and power on. So those are the two things that it joins together. It joins power on and power COM together, just shorts them out in essence and makes them the same pin. So if we bear that in mind and come back down to the power on system, we can see them referenced here, power COM and power on. If we look at power on, All it is a point going to the true ground, so the direct ground of the battery or the DCN, through a 270k resistor, which is R68. So if we look at R68 on the PCB, we can see it here. So you could test that that is 270k or close to. So power on is simply a reference to true ground through a resistor. So it's not a dead short, but it's through a resistor. So when we press the power button on the system, it will short this power comm line here, which is connected to the transistor like here, saying low on, as well as through these buffers and inverters, to the true ground. So how does that turn the system on? So let's start with currently when it's off. When it's turned off, 9 volts comes through here from the battery all the way to the system voltage that says 5 volts, which will actually be 9 volts. Now it's 9 volts relative to the actual battery's ground, so the true ground. But as we mentioned, if we follow the ground along, it's physically disconnected from the rest of the system through Q12. At the minute, Q12's turned off because the gate of the MOSFET goes through this inverter latching circuit here, and by default the state is that it's off. Therefore the ground of the system, the true ground, isn't connected to the ground here, which is to the rest of the system. And if we look at the rest of the system, you can see the reference to ground here, and if we go to like the CPU, we can see it's grounded to this reference ground. So when you first insert batteries and you haven't turned the system on, although there is technically 9 volt potential to everywhere it says 5 volts, that's relative to a ground that the system doesn't have connection to. Once Q12 turns on and it provides a reference to the ground, this would be 9 volts. That means everything in the system would receive 9 volts. The reason it doesn't, as we mentioned, is because once we have reference to ground here, this Zener diode now, which is connected to reference ground, actually has potential back to the battery, and it can dump the excess voltage and regulate it to roughly 5 volts. This isn't a great design because it does mean instantaneously when you're first powering on the system, this 5 volt line will be 9 volts and will drop over time to 5 volts. And if the Zener diode here fails, the rest of the system will receive 9 volts permanently. So it's not a great design, but that's how it's working. So the key is we need to turn on Q12 in order to regulate the output to 5 volts and turn the system on. So when we short this pin here, which is labeled TP18 on low, which on the board we can see TP18 is down here. So here's TP18. This will get potential to the true ground, and if we follow this through, this is just a buffer. So this comes in. If this was pulled high, then it will go through an inverter and be pulled low here, and then go through another inverter and be pulled back high, and then it has a feedback resistor. So this little setup here, which is basically integrated into this chip here. So this is a chip with a bunch of inverters in there. And on the schematic, it's shown as independent inverters. So one here, and then another 4 here. So all those 6 inverters are inside this U6 chip here. So the voltage here gets buffered through these two. So it simply allows it to provide more current. If we follow it along, it goes through all the way to here. Then it goes back through this system, which is first a buffer and then an actual inverter. So it means the output here will be the opposite of what the input here is. So what we measure on low will be the opposite here, which feeds into the gate of the Q12 transistor. So when we say on low, which means and should indicate that when this is low, the system should be on, it would indicate that this gate would be high due to the inverters. If this gate was high, then the MOSFET here, which has its source connected to ground, would have its gate pulled high. Because the gate has more potential than the source, it turns on and joins ground through the system. Once this system has the reference ground connected to true ground, if we go back then to Q7, now Q7's gate can be pulled down to reference ground. As this is the relative difference then between the true voltage input and the relative ground, the potential at this base would actually be how many volts the Zener diode D13 is dropping. So if we were to put 9 volts in and it was trying to regulate it at around 5 volts, we would expect about 4 volts relative on the base of this transistor, for example. Now this doesn't factor in the losses and the current limiting resistor and things, but in general we will see a potential of about 4 volts here. Because the emitter, this power on not signal here, is tied to the main input of 9 volts, and the base potential is now around 3 to 4 volts, this Q7 turns on and stays on. This then latches the system in an on state, and then if we let go and press the button again, remember you are then just shorting the power COM to power on. All that's happening then is you are providing a potential of 9 volts to this point here, because you are joining this point back to true ground and not reference ground. This disconnects reference ground, which if we go back again to Q7, turns off the reference ground here, which floats the base of this PNP transistor high again. This then matches the potential at the emitter, turning off Q7, which ultimately turns the system back off. It's quite a complex little system, and it's hard to explain in a brief amount of time, but hopefully you can take away these principles, and then we will take a look under the scope at this actually happening. When we provide the battery input, there is potential for 9 volts on this 5 volt output. The reason it doesn't actually send 9 volts straight away is because this reference ground is disconnected from the main ground. When we turn on, this reference ground gets attached to the main ground. This becomes 9 volts, and then the D13 Zener diode reduces the 9 volts down to approximately 5 volts. U6, which is the bunch of these inverters and buffers, is effectively a latching circuit that simply turns these transistors on and off independently as we're shorting out the same pad together, one after the other. You don't need to fully understand the inverter circuit, so long as you understand these principles, and I'll show you now how to see this happening under a scope, which you can also just use a multimeter to see. So hopefully that's enough brief explanation as to how this system works. Don't worry too much about fully understanding the schematic, but I wanted you to see the overview so you can see this happening. So what we've got here is I've got 9 volts connected to the battery input. I've got this red wire connected to the ground, and then I've got all of my probes and the bench power supply connected to ground. So we have ground input and simulating 9 volt battery input here. I've then got 3 probes attached. So you can see the 3 probes here. Each of these 3 probes simply attaches to Q7 here, so we can scope out what's going on those pins. I'm then going to turn on the system and turn off the system, and as I mentioned, this device doesn't actually work at the minute, so we should be able to find a problem and go through that together. So you can see we have the scope here, and we have the red wire connected to the on pad here. We have the green that you can't see on the scope because it's always matching blue, but we have the green connected to the base of the transistor, which is this one here. And then finally we have the blue connected to the power on signal going to the CPU. In essence, you can think of the blue and the green as they will always match for the most part. I think the blue will trail the green slightly, but in general the blue and the green are always going to be the high system voltage, the regulated voltage, and the red is the trigger line we want to see. So I can trigger this to turn on by either shorting out pins 6 and 7 underneath, or I can short out TP17 to TP18, which is the 2 pads of the same point, or I can trigger out TP17 to the red wire of the transistor like this. So you can see when I connected TP17 to the red line, it dropped to 0 volts. This should have turned the system on, and what we should have expected to see is the Zener diode kick in. So we should have seen D13 kick in and effectively lower the voltage potentials across these 2 points, and we're not seeing that here. So I suspect already this is exactly the symptoms you will get when you have a bad D13. So let me just quickly test that with meters. So I've just got my meter in diode mode for now. Let's just quickly test a presumably working diode. You can see we have a 0.57 volt drop this way, and effectively an open circuit this way. So let's now test the presumed faulty D13. You can see there we have an almost dead short, a 0.001 volt drop, which is not normal. Let's check it the other way. And again, the same the other way. So this is a faulty diode. This is effectively just providing now a route to ground. So that will mean this diode will be bridging the battery ground to the reference ground, and that's probably why the output then is staying high, because it's never getting dropped by this diode. So this is that exact example I mentioned, where this diode can prevent the system from dropping the voltage, and it can stay at 9 volts all the time. So let me just quickly replace that diode with another one I have. It's not the right size, but I'll just chuck it on now just to see if this works. I've got the power disconnected at the minute to the system, so there's no voltage running through. Just want to move this wire out of the way. So there we have a Zener diode tagged on. That should do for now for the purposes of testing. Let's just reconnect the power. And you can see the scope that jumped back up to 9 volts. Let's now short out the transistor to TP17, simulating pressing the power button. And you can see nothing happens any different either. So if we go to the gate of the MOSFET, we can see we have just 0.5 volts. The source is at 0.5 as well, which means this is not going to trigger because this gate needs to go high. So this gate isn't going high at all. So we've got a screen connected in here. So let's just bypass Q12 for now by just bridging over the source and drain, effectively doing what the MOSFET should do, which is turn on. And you can see that it's actually working. We have insert game. By doing that though, we're just bypassing the whole system, but we're just proving that that's working. We're not really seeing what we want to see. So the issue is the gate of this transistor isn't getting the voltage that we need. Okay, so there's quite a bit more wrong with this board than just the diode. So we'll repair this one at some point and show you how to actually diagnose and repair them. But for quickness, I've just screenshotted a working board to show you what the power on and off sequence should look like. So when we power on in a working board, you can see typically, as we've seen, the red line drops low, and then following that and trailing that, due to the diode working and all the inverter system working, the inputs also drop to around 3.3 volts, which is the voltage drop that goes over the diode. For this to work, it involves U6 and a few other components as well. And something on this board will be faulty other than U6 and the diode, so we'll diagnose that another time. But this is what should happen when it's working. And as you saw with this board, the red line drops, but the voltage still stays high on the outputs. And it's because Q12 isn't getting the high voltage on the gate, which in turn comes from Q8, which in turn comes from other components. So instead of diagnosing all those issues, we'll do that separately. I thought I'd show you what should happen and how it looks. Then when you turn off, the system will be in this state as we see from on. And when you short the pin 6 and 7, or TP17, to the transistor's base, you'll notice that Because it then gets referenced to the real ground, the reference becomes back to battery voltage input fully, and as such then, when the system finishes doing this instability here, which is some of the feedback network, it pulls up high and turns off. This shows you what you should expect to see on the transistor here in terms of the gates. And it also shows you how unstable this whole circuit is and how easily it can die. I say that because I have 3 boards currently in stock, and all 3 boards have issues with the power on circuitry. So I can't actually grab you a fully working board at the minute and show you without repairing them. But hopefully this explains enough that you know what should happen on the power on circuit, and then when we diagnose them next, we can go through all this circuit in more detail and show you the system powering on and off correctly, as well as how to bypass the system by simply bridging the source and drain of Q12. So long as you have a working Zener diode, you can put a working Zener diode here, bridge the source and drain together here, and the system should boot as we tested. This helps eliminate whether the issue is part of the power on circuit or something after that. I think I will also completely replace this entire system with a much cleaner power regulator. So I'll probably be making some hardware for the Lynx 2 soon. So I hope that little explanation of the on-off circuit helped you a little. We'll follow it up by repairing this board. I didn't want it to turn into a repair video. I wanted it to be mostly the explanation of how the system works. So we'll follow up by repairing this board and a few others to show you the system in more detail. But you can see the key principles are a bunch of transistors triggering on and off at the right time, a Zener diode dumping the voltage, and switching the true ground to reference ground. All these components are required to successfully turn on the console, hence why it's a bit of a pain of a system, and people have a lot of power on issues. I will definitely be making a clean power regulator for this system that will cleanly and efficiently regulate the power, as well as probably a USB-C LiPo kit as well. If you want to see me build them live, potentially do hardware videos on them, let me know. But I hope you found at least this information useful, and I'll follow it up with a more detailed write-up on RetroSix.wiki, which is where all the hardware write-ups will go explaining how these systems work.